Hey guys, it's Andrew from Apex Innovation Labs. I'm the founder of Apex Innovation Labs and the developer for ApexAnalytica. It's our flagship building management, energy management, fault detection and diagnostics system that we like to kind of think of as the Swiss Army knife for building managers, for helping building managers, for helping energy managers, for helping engineers try to understand and contextualize their data. We're going to go through each section. There's a lot to get through. We'll split this out into individual videos, but we will have the full video on our YouTube if you want to take a look. But first thing that we'll notice, we have the map of the UK. Doesn't really matter where the sites are. It can be Europe, it can be America, it can be anywhere. But ultimately what we're looking at is a large list of all of these different features that we're going to be going over, as I say, starting with the portfolio overview. We also have these top headers that are effective on every single page. Each one of these headers may or may not be visible dependent upon the role level that you access the platform with. Right now I'm accessed on system admin, so I will see everything. But if you're building level or maybe client level or even organizational level, you might not see all of the different elements. Just want to kind of make that clear up front. But as we're looking at this now, we're looking at the map. Now, with every typical kind of platform, we want to be able to see a statewide. If I've got 50, 200, 300 buildings, in a portfolio, I want to be able to understand what's going on. And so what we're looking at here, if I select this client and go down to a particular client, this client has 6 buildings within the UK. And so really what we're looking at is what energy data. So in this case, we're looking at electric meter data. And we're looking at the last 30 days worth of energy. So you can see how much energy is being used in the last 30 days, what the cost of that energy was, and what the carbon, tons of CO2 has been released as a consequence of that energy. Now, one of the things that you'll notice is we can clearly see in the last 30 days, it's actually gone up by 27.4%, both in terms of cost and electricity. However, with carbon, it's gone up 67.6%. Now, the reason behind that is, we don't use the standard UK government factor of, for electricity, something like 0.233 or 238, whatever the standard government factor is. We take the grid supply point of each individual site and the carbon factor, which changes every half an hour. And so it's important distinction to make, because for every kilowatt you burn is purely dependent, in terms of the amount of CO2 that you give off, is purely dependent upon how clean or dirty the grid is at that point. So how much solar, how much wind is available will determine how much carbon gets released based upon the amount of energy you use. And so that's an important distinction to make, why that figure is different from these figures. We can hover over each site to give some information about that site in terms of the energy that's used in the last 30 days, specifically the live current temperature and the next 7-day forecast. Then we can move, as well as this, we can then have a client performance tab. Now, the client performance tab gives us a league table of how well each site is doing, or each client is doing, in terms of a league performance. The main barometer we use is energy intensity, which is kilowatt hours per square meter. Just gives you an idea on how well each client is doing in a table format. Next, we move into building analytics. Now, building analytics gives us a relative scale based upon, again, energy use intensity. And the reason this is powerful is because what we're trying to understand from a client-wide perspective is how well is my particular building doing relative to the rest of the portfolio. And as I hover over these here, what you'll see is intensity, so 7 kilowatt hours per square meter. These ones down here are 5 kilowatt hours per square meter. Over on the right-hand side, that's like 63 kilowatt hours per square meter and 75 kilowatt hours per square meter. So the obvious question is, if we're measuring building by building and how much energy is given off for every square meter, it's a much cleaner way to benchmark sites, because if the buildings are the same, then we should anticipate that kind of bang for buck, that they should be relatively similar, and if they're not, there's a reason why. And so we want to put our focus and attention on these particular buildings. Now in this case, it's doing every single building, irrespective of whether one's an office, one's a retail, one's a a factory, or whatever else. But here is where we can finesse it down to the building type. So if we've got, as maybe warehouse general, what this will give us is all of the portfolio buildings that are all of this criteria and type, and again will give us those same pieces of information, so we can again try to figure out which ones we want to focus on in terms of the priorities. We also have the ability with this to look at different benchmarks. So this is a relative scale, so just benchmarking your portfolio. But in this instance, we can go down to something like net zero operational carbon, and we can see, based upon the statistics of how they put together their benchmarking, which ones actually fall within different criteria. So, for example, for a typical office building, for net zero operational carbon, they say anything less than 55 kilowatt hours per square meter is considered excellent. Obviously, less than 70 but above 55 is good. Less than 85 but better than 70 is between average, and then beyond that is considered poor, right? And so again, as I mentioned before, it's a different way to look at ways to understand the building characteristics and which ones you want to put your effort and focus on. We have these guides throughout the platform that explain what is it we're looking at, because we appreciate that not every piece of information will be easy to understand, and so we have this guide notes that are kind of littered throughout the platform. Kind of moving away from that, if we now go back into the dashboard, what we're now looking at, if this is the portfolio overview, so looking more around like a statewide, here we're looking more at the individual site. And so this is a particular building A, right? And so within this building, we have KPIs, as we do with the wider, a statewide view. We have carbon emissions, again, relative to the actual carbon used, not the UK government factor. How many active alerts and what the total energy cost is. You'll notice these cards or these toast notifications keep coming through. We'll cover them in a short while. So energy, this is showing the last 30 days. Each one of these blocks is essentially a full day's worth of energy. And we have a grey nested bar in the middle, and we have the coloured bar on the outside. And what they represent, the nested bar, is the same previous period in the last year. So right now we're looking at 2026's data. The grey nested bar, so for 21st of January, the grey nested bar is the 21st of January 2025. So proportionally against its previous year, how well did it do, today against the same day last year? And the colours will be representative based upon green is it decreased by more than 5% compared to the same period. Amber is within a 5% tolerance, and red is it's used more than, or at least used more than the last 5% of its previous year. And again, we have these documented guidance throughout the platform. We can actually go right the way to all time. So I can see here the last 4 years worth of data. I can click into that. That will show me the last 12 months. I can then click into, a month, and that will show me the weeks within that period. I can then drill into, a week, and it'll show me the 7 days within that week, and right the way down to the half-hourly performance of the 48 half-hourly data points. We can also show that as a heat map. Like with any heat map, really what we're trying to train our eyes on as a visual indicator is the kind of operational hours. You're expecting more visual heat, if you like, or more high intensity use during operational hours. But what we're trying to identify is these outliers where clearly assets have been running out of hours during these periods, to identify that. Moving down, now we move into the forecast. So this is obviously the histrionics, the previous data, all the way up to today. So if I go back to, say, the last 30 days, this is today's current data, which we're getting every half hour, right up to 11 o'clock. You can see it's currently 11:25. So every half hour, we keep on adding value to this. But what this gives us is the next 7 days. So with the next 7 days, what we're trying to articulate, because we can collect data, and on this particular data, we've been collecting 768 days worth of data. What we're able to figure out based on weather and energy is what the optimal range conditions are for this particular building. And so what we know is between 18 and 23 degrees is really the sweet spot. That's where the correlation between least amount of energy is given off when the ambient conditions are between 18 and 23 degrees. And that gives us a little bit of an inclination as to how we can forecast the next 7 days. And so you can see here, as an example, how does weather impact the next 7 days? Well, if we think between 18 and 23 degrees is the sweet spot, 7 degrees is effectively going to be a rather large impact in terms of how well this building is insulated, in terms of how it uses data. And so, you know, we factor in kind of a little bit of secret sauce to then create our machine learning models, which is constantly evaluating data and then feeding itself back in to create what the next 7 days look like. And so we know, as an example, on the 9th of February is a Saturday, 7th of February is a Sunday, and so within those 2 days, we're expecting just a low baseline, because we expect the site's closed based on the occupancy period. And so we can see, you know, what's the expected total consumption over the next 7 days, and what's the total cost of that based on the tariff rates. But obviously, if we can forecast 7 days into the future, we should be able to analyse the last 7 days in the past as a rolling 14-day period. So 7 days ahead as a forecast, 7 days behind to evaluate that forecast. And here's our accuracy model. And so what we can see from this information is a number of things, right? So here is where we're taking the weather prediction for the forecast against the actual. And so you can see we are actually pulling the data directly from the local weather stations for each individual site. But what we know about this particular building is it's closed on a Friday, closed on a Saturday, and closed on a Sunday, theoretically. But what we're actually seeing is, although our forecast expects it closed and using a minimum baseline, what we're actually seeing is real energy being used. And so there's a disconnect here. Either the site is running when it shouldn't be running, or things aren't being switched off, or they haven't updated the schedules in terms of the prediction model to allow the predictions to be precise. I'd probably suggest it's the former, where the site in itself is running utility when it shouldn't be. And so what the prediction model gives us is the accuracy gives us is what we expect in purple, predicted, versus the actual in green. And then it lays out that as a table. So it tells us what our predicted energy is versus the actual, the accuracy when we predict that data. So you can see the 3 days it's closed, the accuracy is right out, simply because we're expecting relatively low baseline, but actually it's using a lot more energy. And so the cost difference really matters for those 3 days. And so what it gives is, because we're also bringing in the tariff data, is what the difference is against that model. So it's a really nice way to kind of predict the next 7 days and then evaluate those previous 7 days. As we move down into the into some more of the kind of technical stuff, now we want to understand a little bit about how our building has been operating. We'll cover this in a second, but I can ask you basic questions, right? All really complex questions, but I can say, you know, please provide me insights into my building over the last 7 days. And now, Ask Apex is our feature, is throughout the platform. It covers everything from FDD, QSUM analysis, energy, reporting. You know, so what you'll see is it's got access to a lot of different data, a lot of the tables within the database, and a lot of the API endpoints that we give it access to. It has guardrails, so it can't go out into the internet. You can't ask it you can't ask it silly questions like, give me the stock price of Apple. It really understands only information about this building. Now, for obvious reasons, we have give it fictitious data in terms of the address, because from a GDPR perspective, we want to make sure we are not displaying anything uncharacteristic. And so here's the information, right? So building 7, energy performance, last 7 days, overview. So how much consumption is used, what is the daily average, and the estimated cost of that data, of that energy, and what the current carbon emissions were for those 7 days. Some key significant variations. So the highest day was 223 kilowatts, the lowest day was 102, which is 180% variation between consecutive days. Highly unusual. Some critical equipment issues. So both chillers are experiencing severe operational problems. There's 19 critical faults for equipment protection. Chillers running without detected chill water flow. It's also detected that there's some warnings that chillers are operating outside of operational hours. It also knows that there's a new fan coil unit on the second floor may be affected by these chiller issues, and we'll come to that in a second. It's also identified excessive after hours use. We're probably seeing that, right, because we can see that there's usage happening when the building should be closed. So what, 85 energy anomalies, 67 critical severity. Weather context, so it is kind of understanding that the average temperature is around 6.2 degrees, relatively mild and stable conditions, and weather doesn't explain the consumption variation or after hours usage. So this is really around just a brief overview on asking to provide some information about my building. So we've asked for the last 7 days, and that's provided that information. I want to talk about this in a later session because I think it's a really powerful thing. Next, we're going to go into FDD, fault detection and diagnostics. So with this, what we're really doing is pulling in data over a BMS system. And so the way in which we can get data in is a number of different ways. You can see we can pull BACnet over IP. We can do it over Niagara. We can do it Modbus TCP, MQTT, database for older systems where we have a SQL Server database as an example, and over REST API. And when we pull that data in, what happens is within the BMS discovery, I can go protocol discovery, bring this data in, and then we see a station list. So here we can see we have a number of different folders within the station. And we can see we have boiler house, roof plant room, energy meters. And what we can see here, if I go into the point list, across those folders, this is telling us all of the available points that we can pull in to the system. And that's a really important part, which we'll go into as to why that is the case. And so what's really powerful here is if I have a sub-meter that's part of a BMS system, I can select that as a sub-meter, register that as a meter, and then, what floor it's on, the utility type, register that as a meter, and then that would show us a sub-meter as part of the main energy monitoring. So we don't just need to take energy meters from suppliers, we can also take it directly from BMS systems as well. The reason this is important is because once we get that data, we can do really smart things, like we can create relationship maps based upon parent-child relationships. So in this instance, what we're looking at is we've extracted data from a BMS system and then using nothing more than connecting these data points, so creating that parent-child relationship. The reason it's so important is for root cause analysis. What we want to be able to do is in split seconds, not in days or hours, is be able to quickly have our system review and provide us an analysis based upon what it's seeing. And so here you can see right now we've created that parent-child relationship. So we have chiller 1, chiller 2. The children of those are coolant tower, chill water pump 2, chill water pump 1. And then the children of these are things like your AHU, your VAVs, your fan coil units, your kind of end terminal units that would be considered on a chain between parent-child relationships. And again, for root cause analysis, our FDD system has a load of rules that we've created that are mechanically based rules that takes a snapshot at every moment in time whenever a rule gets broken to provide that analysis in seconds. As I say, you know, a typical engineer might, it's really warm in an office, get a call out, engineer comes to site, first thing he does, pops his head above the ceiling, checks valves, or maybe on a fan coil unit, sees the valves are operating okay, sees the fans running okay, then has to go and maybe check that there's a zone valve somewhere in the ceiling, he's moving those ladders. He then figures all of this out from kind of endpoint all the way back to root cause, which might be, you know, a valve, a 3-port valve that's maybe stuck in a plant room or whatever it would be. What we do is we take a snapshot instantly, and we have our Ask Apex do the analysis straight away, and it provides a lot more context to that data, which we're going to show you in a short while as you continue seeing that. So really powerful relationship map that we create. But then kind of the key to this, go back to a different build in a second, is obviously we're creating this data, we're pulling this information in. You know, we can look at the trends, we can look at all of the different things over the last 24 hours or last hour or last 7 days, but it's surface level stuff, right? Really what we want to be able to do is really get a deep understanding of what's going on within the system. And that's where we come into our FDD. So what you'll see is we have a load of rule types that were concentrated on, aligned to guidance standards. So typically we use ASHRAE Guide 36, but we also have other guidance that we can use like BISRIA and SIBC. But you'll see we have all of these rules that we've created ourselves aligned to ASHRAE Guide 36. And what these rules are is basically once we collect the data from the BMS system, our rules run in the platform. And it's really powerful because we don't need to rely on haystack tags. We don't need to rely on brick schema. We do all of our relationship and point mapping in the platform, and it's done to a level which, once we create the asset, means that we don't need to rely on that level, formulated level. And that's because for us, and the way we think about it, is we don't want to be reliant on engineer mistakes, you know, incorrect tags being introduced in terms of the hierarchy. And so what we do is we take away all of that issue. And the way we do it is quite simply, is within a particular building, we go rule coverage. So I can see here, if I select all assets, all of these assets have been mapped. This boiler and this boiler needs 1 point to be mapped. If I go into configure, I can see rule analysis. All of these are ready and mapped, but we have boiler enabled, no flow. So in order for us to be able to map this particular rule, I need to see, firstly, what is the rule? What is it looking for? And then what points are required? And so here we need low temperature hot water flow switch. And so what I need to do now is in the database that we've pulled that information back, which we've discovered, here is all of the points. And so the mapping concept is that I look for the flow switch, and then I just simply map it. So as an example, this particular building doesn't have a flow switch, but if it did, I would simply select tick and then click save. That point has now been mapped to this building. Okay, so that's the flow switch. And once I've done that, that rule's mapped, and then all of the rules that require that point also get automatically mapped as well. And so you can see the real power and efficiency in being able to map points relative to the rules. So on one side we have the rules. The rules require points to be mapped. We then collect the database and we pull that data in. Nice and easy, as simple as that. And then what happens is once these rules are all in the database and we're mapped across, we start to generate alerts relative to these rules. So if I go into the alert section here, here's these genuine alerts being actioned. So I can see here, you know, low delta T. What's low delta T? Low delta T is where we're supplying hot water or low pressure hot water to the system at 80 degrees as an example, and it's coming back at like 79 or, you know, within a 5 degree tolerance, which means the system is not taking the heat. And so it's inefficient way to run boilers if there's no demand being led from the CT circuits and the variable temperature circuits and hot water systems. So what I can do is I can ask Apex about this particular alert. So the rules being broken. It's generated an alert. I now need to ask Apex, tell me the context of what's happened during this alert. So now it's going to review not just the data, not just the FDD fault, but all the data that it understood about that time during that exact time that alert was generated. So once it's done its analysis, it will provide us that detail. And so here we have it, right? So, on at 11:33 on Wednesday, the 4th of February, which is today, the boiler system triggered a low delta T warning with both boilers enabled on low temperature hot water flow at 80 degrees. The system achieved only a 1 degree temperature differential. So you can see we're supplying at 79 and we're coming back at 78. Despite active heating operation, this occurred during scheduled hours with an outside temperature of 4.8 degrees. The data reveals both boilers are enabled with a flow set point of 80, yet the actual flow temperature is 79 degrees with a return of 78, an extremely minimal 1 degree difference. This pattern has been recurring consistently, with 5 similar faults already triggered today at 5-minute intervals since 11:02. The building's energy consumption shows significant activity, 22.39 kilowatt hours at hour 11, indicating the facility is operational. The outside temperature of 4.8 suggests legitimate heating demand should exist for this warehouse facility. No pump speed data is available to confirm overpumping directly. The 1 degree delta T strongly suggests the heating water is circulating through the system with minimal heat extraction. This pattern appears most consistent with either number 1, no zones actively calling for heat despite the boilers being enabled, causing water to circulate through a bypass or low resistance path, or number 2, a control logic issue where boilers are commanded on without corresponding zone valve opening. The recurring 5-minute fault pattern suggests this is likely a persistent control issue. And then it gives us a kind of a root cause analysis confidence level. So 95% confidence that the boiler appears to be responding to a heat and demand signal that isn't matched by the actual zone valve positions. And so it's a really nice kind of way. And what I can do from this is, after this analysis, I can create a work order. And so I can create a work order. What it'll do is I can assign it to an engineer, or I can just create a work order as is and then assign it later. Once I create that work order, that gets stored in the system. We're going to cover work orders in a short while. And so what's particularly powerful about this is, from our side, we have obviously all of the rules that are aligned to really solid industry standards, ASHRAE Guide 36, BISRIA, and CIBSE. And what we're looking for is how well does the system perform relative to these standards. And what's particularly powerful, we don't just stop there. If I go into control logic, we're now mimicking what we're seeing in the BMS system with the way in which we extract the data. And so I can go into drivers, and this is connected to a live site. I can go into boiler house, and I can see here that we have actual data. We have actual information about the BMS system, what's going on. Now, this is typically logical sequence, and this is BMS orientated. It's what a BMS engineer would draft or write for how a system should be controlled, including things like safeties, demand signals, occupancy periods and stuff like that. And so what we can see here, that both boilers are running. But what we're interested in right now is how good is this software? And like I've said throughout the actual platform, we have Ask Apex. And so for the first time, we're now able to take away the technical burden of understanding control logic, which is a BMS orientated task, into the everyday request. So I can say Ask Apex about this particular strategy. And so what we've got to realize here is this isn't strategy that's been drafted by this platform. This is strategy that's been designed and curated by BMS companies, maybe against the specification, maybe it's been modified over the years, who knows, right? We're not interested in that. What we're interested in is how well will it stand up to scrutiny of ASHRAE Guide 36, of CIBSE, and of Bizria. How well is the current software in my system relative? And so I can ask a number of poignant questions. Like I can say, give me a description of operation telling me how my system is currently operating. And so now, like with everything, it will go off and analyze that data. Now this is connected to a live site, so it's going to analyze every single link within the system to understand how and what this building is. Now you can see here in this drop-down menu we have different ways in which we can articulate. So exec brief for non-technical people that just want to know the highlights. Tell me about my system, what it is. The operational view, more for kind of facility and asset managers. And then we have the engineering detail. So if you're a BMS engineer and you want a quick understanding of what's going on without having to go through the logic, it'll give you a much more detailed visual. And so we can see here what this controls. You know, this is the main boiler house control system managing 2 boilers that provide heating hot water to the building, along with associated pumps and mixing valves. The boilers operate during scheduled hours between Monday to Friday, 6 till 6, when the building is occupied. Both boilers turn on together when the heat and water temperature drops below 80 degrees. Switch off once it's warm enough. The system has a manual override, boiler plant enable, that allows facility staff to turn everything on outside the normal operating hours if needed. There is a variable temperature circuit with its own pumps and mixing valves that can provide lower temperature water when the boiler temperature isn't needed, etc, etc, etc. So it's given us a description of operation based upon what the logic is showing it. Now that's okay, but what we don't know is that right? Is it wrong? Is there more efficient ways to actually control this based upon the inputs and outputs that we have, like the sensors, the boiler enables, the safety measures? So I can now say, analyze this data and provide me an update on how well it's been articulated or it's been drafted. So now it's analysing it. We created our own scale. It's a 5-star rating based upon how well we believe the engineered software has been rated. And you can see here it's base. It's 2 out of 5 ratings, right? What are the major deficiencies found? There's no weather compensation. So outside air temperature sensor exists but isn't connected to adjust flow temperature set point. System runs at a fixed 80 degrees regardless of outdoor conditions, wasting significant energy. There's no staging between the boilers, so both boilers enabled simultaneously rather than staging based on load. This causes excessive cycling and inefficient part load operation. There's no lead lag, so both boilers always start at the same time. There's no pump rotation. Fixed set points have only been observed. There's no trending or diagnostics. Basic on-off control, and immediate improvement needed. So we can ask some really poignant questions. Now I can also, because this is two-way communication, I can also write data. So what becomes really powerful here is that within the system, let's assume within the system, for whatever reason, there is a fault. Right now we can see that the system is true, boilers are running, but within, let's say there's a safety error. Now I'm going to manually override this, right? But let's say for some reason there's a safety issue, which has meant that the boiler safety is now gone as an issue. What will happen is we refresh it every 60 seconds. So within 60 seconds, you'll see the boiler safety, which comes from here, will go false, meaning there's some boiler safety issue. And then from us, we'll see that the boiler enable 1 and 2 will go off. Now, what happens in much more complex logical sequences is there might be a number of these different areas that can be off or cause a problem, which is why the boiler won't run. Now, the first protocol to any type of facility manager is to raise a call, with hope it might be a remote dial-in. But if that's not possible, it's an engineer to site. It's raising work orders, it's delay. It's all these issues that tend to arise when you have to get something looked at quite quickly. But with the power of Ask Apex within the logical sequences, we can now, in a really simplistic way, ask it basic questions. So the interactivity, so we're able to write data back down to the BMS system. We're also able to read that data back into the BMS system. Whenever a change occurs, like maybe a schedule changes or a set point changes, it happens instantaneously. We refresh it every 60 seconds, and then on that refresh, It just the visual representation will change after 60 seconds, but the actual will change instantaneously. Now we can see boiler safety here has gone false. The 3 AND statements requires 3 true statements, but the bottom one is false, which is now why the boilers are off because of the safety. Now this is might be an area that you might not see this in, but I can go into Ask Apex and I can say, why are my boilers not running? Basic question. You might not know the answer, but now we can ask that question. So now it's analysing that piece of information. Why aren't your boilers running? Looking at the control log, your boilers are off because the safety interlock has tripped. The boiler safety signal from the roof plant room is causing false. This blocks the boiler enable signal, even though everything else is calling for heat. What's calling for heat? The time schedule is active, the temperature is below the set point, but the safety interlock is blocking it, which is why the boilers aren't running. What you need to check: go to the roof plant room, investigate what's tripping the boiler's safety circuit. Common safety trips include gas pressure fault, flue ventilation fault, emergency stop pressed, fire alarm interface, high temperature limit exceeded, low temperature. So you can see now this gives. And we've done nothing more than expose the logical sequence of how a typical system operates, legislated by exactly what's in that control system. So we haven't drafted this software. This is software that's been extracted into the platform, and it's live data. So any changes that happen locally also get reflected remotely. So we can analyze this data every single time a change has happened, when a service is being completed, when some change to the logical sequence has been completed. Maybe you want to optimize that software. You can then review that data. You think of consultants who need to understand if a specification's been adhered to, does that actually run to a specific requirement that they put in the specification? All of this kind of stuff has now become powerful with Ask Apex. So that's a really powerful tool. This is only exposed to roles that require this level of integrity. We provide a full audit trail of everything that happens within the system when it changes, who's wrote that data. You can see here that change that was made for the boiler safety is all tracked within this data. And so you can see from an FDD perspective and a controls logic perspective and a real way to understand how the system's operating, it gets more into that kind of blurred line between really technical but really basic, being able to ask it simple questions about how that system is being operated. As well as this stuff, we also have wellness, right? And so on a particular, if we want to, right now that we've got no gateway set up for this particular building, but we have in this building. And so in this instance where we have information, we can show that data specifically on a building. So you can see here, make sure I'm on the right sensor. So floor 1, let's do reception. You can see here, we have like CO2 levels. These are mile site, AM319 sensors. They provide a lot of data that comes through, usually 9 or 10 in one sensor. And so this is where you might have a sensor in a specific area. What we do is we align the standards to well certification. So we alert, you can see the color gradient. So green is obviously good, and red and kind of amber is not so good. What we do is we alert in the database and generate an alert if the temperatures, the CO2 levels, if the particulate matter, humidity levels are outside of what we expect in terms of a well certification. And so they will be triggered at that point. We also include dew point calculations, which allow us to know when specifically fabric protection should be introduced, because the temperature drops below the dew point, and therefore condensation in a specific area where the sensor is located is got the potential to generate moisture, therefore mold and everything else in and around that. So really powerful stuff with that. Energy generation. So here we are pulling in data directly from a CHP. We can do that over CSV, or we can do that directly via Modbus over IP as an example, which provides a lot of information. So here on a CHP, the most important factor for us is the total efficiency. So how well is heat and thermal and electricity being generated? You always want it to be the lead boiler, obviously for obvious reasons. Look, tracing its power output over time, looking at its revenue cost breakdown in terms of being able to supply electricity against the cost of gas and heat, cumulative profit in terms of how much it's actually saved, availability, obviously another big one. And so we have this really nice way to track things like CHP, solar and wind generation. One of the other fantastic capabilities of this particular platform is our ability to track and manage energy conservation projects. So a typical energy conservation project might be, solar's been installed, maybe you've installed or replaced some chillers, maybe you've done some LED lighting, be a number of different things that happen within a building. But what you often want to do is track the process in terms of how well that project has delivered on its business case. And so here, in terms of how we manage this, we're loading up the entire energy profile over the last 5-6 years of this particular building. And with any kind of business case, you want a baseline on what a typical baseline might look like in terms of normal. Now you can see a big drop off here. Clearly, something happened within this particular building that generated those savings. Well, here's where you'd put in your information: the base period, the end date, the start date, the measurement period. So the baseline period is the period that you want to measure of what normal looks like before any energy conservation projects have been happening. The measurement period is the period after those energy conservation measures have been installed, so you can start to track the true value of what that investment cost and savings start to look like. Here's where you put in the information about that energy conservation measure, and then the financial projections given to you by the supplier who's doing that works. Once you create that ECM, we then track that in real time, right? So in projects, we have a number of different measurement models. So we have 3. We have IPMVP based weather normalization, so using heat and degree day regression. What we're looking for is anything above 0.5 R squared line of best fit. If the outdoor conditions don't have a net effect on the building, you'll generally get a flatter line. And so we have our own unique algorithmic developed models for daily average and seasonal patterns. And so here we can see a seasonal pattern. So we've baselined this data in the past of what normal looks like, and then we've used the model to forecast what the future would look like if we continue on that trajectory. Now this grey period here indicates what that model has projected, and really what we're looking for is, does the forecast represent the past? If it looks very similar, we can almost, with some decent level of measuring stick, suggest that this is what we expect the energy to be at if we don't do anything favourable on site that reduces energy. So in this case, where we see this big drop of energy, that is after the ECM was implemented. So after solar was installed, after the chillers were replaced, after a whole host of filling the missing blank has been done, we see this drop in energy, and then we're able to track that in real time against the implementation date. So in this case, the investment cost was, say, 75k. We anticipated the saving of around 55k per annum in terms of the savings, and here showing a 1.4 year period payback, and then the actual savings to date relative to where we are. You can see here we're up to date. So this is a live tracker that tracks that project in real time. If we have multiple projects, they can update. We see, they get added to. So we'd have another ECM that gets added as an ECM line. So this one might be, chillers replaced. This might have another one here that says LED lighting replaced, etc., etc. So really nice way to kind of track projects in real time and check them out on different models to see which one fits best. We also show the performance. This is more detailed and showing you these in different ways. So again, similarly to what we saw in the first, we can see over time, how the baseline reacts to the actual consumption and the savings. So the blue line is the actual consumption dropping. The energy savings is the green line going higher. Against the baseline is the dotted line here. We can look at that as a stack view, a waterfall view. So here showing the actual against the baseline, and the green showing the actual saving. So green in this case is a saving made. If it was up here, it'd be red, which is not what we want to see for obvious reasons. And then we have a timeline view, so the cumulative overall consumption reduction as it's saved over time. So really good stuff. We can also look at models. So you can see here, this is all time in terms of the correlation between heating and cooling degree days against temperature. So you can see this building particularly doesn't measure well in terms of efficiency. So you can see, like here, you know, it's minus 4.1 degrees and we are using 871 kilowatts. So you'd absolutely perceive this as to be a heating season, but still using around 871 kilowatts. As in over here, when it's like, you know, 19.6 degrees, we're still using 990 kilowatts. So what this tells us is seasonal variability doesn't really factor in. The consumption in the winter is just as high as the consumption in the summer. So weather doesn't influence this building too much, which is why back on the projects tab, you know, if I was to change this model to the IPMVP certified regression model, you can see it's quite a flat line. And that's because weather doesn't correlate much with this building, which is why we developed a number of different ways in which we can model the behavior of the past moving forward into the future. Next, we can come on to performance tracking. So again, with this, this is Q-sum analysis. So there's where we provide a particular year for the baseline. So in this year, this has got since 2022 was the baseline year. Was a normal year, not too much activity happened, pretty seasonal. And so what we do is we track over the next 4 or 5 years how well the building performance goes over that year. So you can see the blue line here is the actual energy data. And then we see that big drop off as we know on this particular site. But that happened in November 2023. Now remember, we're baselining against 2022. So the start of 2020, end of 2022 to start 2023, the expected, which is the purple line, the actual was a lot higher. And so this deviation, this red line, shows how well you're performing to your baseline year. So you can see it starts off pretty bad on this particular building. Then they get that big drop off where they've done some energy conservation measures. And then over time, the distribution or the deviation curve starts to come in. But it actually measured against 2022 took all the way up until September 2024 to get that negative overspill from that first part of the 2023 down. So even though the saving started here, the realization catching up from 2022 took the best part of 2 years to come in, which is kind of really good analysis to show you what's going on. Now, of course, we show that's history over time. We show a rolling 12-month a rolling 12-month view and a rolling 30-day view, again against that baseline. But also we can ask some information. So obviously this is quite complex stuff when you're getting into the energy management and trying to realize what you're dealing with here. So we can ask, tell me a little bit about my site, right, in terms of that consumption. So now it's got access to the same data, but it's going to give us more of a articulated understanding of what's going on. So we can see here, significant energy reduction achieved despite weather-independent consumption. We mentioned that, right? It's not really relative to the weather. The building has reduced electricity consumption by compared to the baseline of 2022 with zero correlation to outdoor temperature. So it's really no correlation. This indicates the savings are from operational changes rather than weather variations, suggesting successful implementation. Electricity usage completely decoupled from heating and cooling demands. So just a nice way to kind of give an insight into what information it's seeing on that kind of piece. I mentioned earlier on that we don't use the UK government standard carbon intensity factor, and instead we pull it from the local grid supply point for each individual zone. This gives us the unique advantage of being able to track the 24-hour or 48-hour period, 24 hours in the past here, and 24 hours into the future here about carbon intensity, so we can see what's the idea here. What we're trying to provide is an understanding of how carbon intensity throughout the 30-minute periods throughout the day gives us the ability to load shift or carbon shift. So can we try to match our higher usage requirements during lower intensity periods? Because obviously what that means to us, or you as a client, is that you give off less carbon for every kilowatt you burn when intensity is low. So in really plain English, it's more greener. The local grid supply point that is powering your building is greener, using more less fossil fuels, more green technologies during these periods. So can you start to carbon shift around those periods? And kind of a nice way to kind of give that. Peak demand analysis, this just gives us the highest amount of energy that was the peak demand in that particular hour against the average of that hour. So how much energy was used as a peak. Sometimes you can get really high startup power consumption that can affect, and if you're on a tariff that gets hit with the high peak demand, you're trying to avoid that. So you want to try and see what your peak demand is here. We also have anomaly detection. Now this is the last 7 days worth of data, and what we're trying to detect is anything. We use a machine learning algorithm here again, which you feed data back into. So I can click on a particular day, and this is identified this particular day, and I know why. It's because it's the day when it expects, on a Saturday when this building should be closed, that all of the in-hours operations are considered anomalies because it shouldn't be using that. It shouldn't be using energy. It should be more closer to here, right, which is the baseline, which is what it expects it to be for the base load. And so it will highlight these as red. If we pick a day, like maybe Tuesday, when we expect the system to be on, it's going to pick those high ones that is outside of what it expects over a 12-month period. But it uses a lot of really concise data: hours of day, weekend operations, occupancy period, standard deviation of consumption, and it looks at all of this data to determine if it determines that it's a high critical anomaly. And then within that, again, we can click on this. It identifies which anomaly it is, and then I can ask Apex to provide context. What happened during this spike? Now on a main MPAN, what we're trying to understand is, if it's difficult, if we don't have sub-meter data, how can we articulate exactly what caused, or not exactly, that's not right commentary to use. What's the probability of the net result of that spike? And so like Ask Apex for FDD, we also have Ask Apex for anomaly detection, and this is purely on consumption, whether that's electricity, gas, or water, or whatever it would be. And so now it's going to analyze that data, and we'll see what it comes back with. Okay. So looking at this electricity anomaly of 0.7 kilowatts on noon of Tuesday, I can see limited BMS data from 5 pieces of equipment. The chill water pump showing 13 kilowatts of power draw and has a fault status of 1, indicating a fault. Whilst the pumps show 5.5, these are the only power readings I have. The chiller is running, but I have no power data for it. The AHU is at 47 fan speed, but no power readings. Critically, I cannot see lighting systems, small power loads, IT equipment, or any other electrical consumption that would typically exist for a 75,000 square foot office building. The pattern shows similar anomalies occurred multiple times in the past week, blah, 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 blah. And so its confidence level is relatively low. It's got medium confidence. So the more information the Ask Apex has, the better the output. But you can see it's going to provide information about what it sees. So it doesn't know whether that high consumption was due to the fact that the chillers are running, because it doesn't have the energy data for that chiller. But it does show some evidence. Both pumps show fault status. BMS, chill water drawing 13 kilowatts at a speed of 43% historic. What it wasn't, boiler 1 gas fired, obviously it's because it does not contribute to electrical consumption. Weather driven load at 4.5 degrees heating would be expected, but this wouldn't cause electricity spike unless electric heating was present. And so dependent upon the information now is where it becomes really powerful. If I've made an incorrect assumption about your building's equipment or operations, please let me know so I'll remember for future analysis. So here we could say, after some research, I identified that, you know, a fan kicked in at this hour and it's not on the BMS system. And so it would catalogue that for future reference. And where this becomes particularly powerful is in the building knowledge. So if I go to building IQ, this is where all of the magic happens, right? So what is building IQ? Your building's intelligent profile. And so the more I learn about your building and assets, the more accurate my analysis becomes. Answer what you know, skip what you don't. Every bit helps. So tell me about your building. I'd love to learn more about how this building improves to improve my analysis. So here's the things I already know: weather data, operating schedules, tariff data. I know 9 assets, and 8 of them have got specifications for them. And I've learned 17 facts. Things that help me: the building type, major processes or equipment, specialist equipment, recent changes or known issues, occupancy patterns, and peak usage time. So I can type in things like FCU unit changed on the 2nd floor outside the lifts. Just useful information to understand and store. That gets stored. So now it's just going to run that through, and that information is now, it's a 1 fact learned. If I go into the knowledge here, these are all the facts that has been learned over time for this particular building. New tenant on floor 3, September. They're a 24/7 call centre. Floor 14 is a trading floor. They start early at 6:30 p.m. and have extra cooling needs. The reason this is powerful is because every time an analysis is performed, it reviews all of this data first to give it more context about the building. What assets it's got data for, so I can see in the specifications, like if I edit the spec, you can see here, this is a VAV, it's electricity, the performance, operational and life cycle, the date the warranty expired, last service date. So all of that information can be provided to really provide that powerful data. And where it becomes particularly powerful is the document storage, so that golden thread. And so right now I can upload the document, give it a title. It can be an O&M manual, it can be a BMS schematic, it can be a heating schematic, cooling schematic, ventilation schematic, control sequence, wiring diagram, whatever kind of documentation is relevant to this building specifically is where we add this data here, and we just simply drag and drop it. That stores that information in our vector store, and then every time an analysis is performed, again, it has access to that data. This is at a tier 1 level. This tier 1 is individual to each building, and each building will only have access to its own data. We also have a tier 2 data. This is a global documentation storage. So here is where we have things like ASHRAE guidelines. So the ASHRAE guidelines is ubiquitous to all buildings because we feel it's a really powerful standards for how buildings should be controlled and managed in terms of their efficiency for sequences of operation. And so that gets access at the global level, but at a building IQ level, this is around the individual building itself. So really powerful stuff. I mentioned earlier about work order management. So within the work order management, you can see each time we can generate a work order from an FDD fault or an anomaly, but we can also generate a work order just as a new work order, right? We can give it a description, we can give it a title, we can assign an engineer, we can add it to a building. When we go into this information, if I go into view details here, I can see that this is the one that we created earlier. This is the history, so I get the analysis from Ask Apex about what it determined during that FDD fault. You know, I can add a note here, and I can say John Smith has been assigned to this. That note gets captured and timestamped. If John Smith comes back and then says, actually, I've realised the issue is a Belimo actuator sticking. I'm not sure what the part number is. you know, you can ask questions here to Ask Apex. So that Ask Apex then goes and does the research on a particular Belimo actuator, and then get you a list price for what that actuator is. Obviously, buildings may have, or clients may have their own deals with different suppliers, and if we have that, obviously that goes into the document storage, so the next time we need a new actuator and the part number, it's already got access to that data. So this is really around the power of bringing AI into our document storage for that ability for you to track that. If there was a particular part, you can add that part here, what the unit cost was, the supplier, that then gets stored. And then lastly, we have the ability to upload a report. So if the report mentions what the fault was, how it fixed it, and you know that information, it then gets stored as building knowledge again for Ask Apex. So it's able to review that data each time an analysis comes through, and the intelligence just builds over time. So we've covered the alerts. Really powerful alerts. They can be, in terms of how they can be distributed, so in the alert settings, they can be based upon system-wide, all clients. So you can apply these rules. What I mean by that is we define the criticality of each individual rule. We define the criticality of wellness in terms of how critical each metric is measuring. Anomaly detection is automatic, and then in here we determine to a particular user may only be interested in critical alerts, and I only want to receive emails for critical alerts, and I only want to receive them in the app. So they would just tick or untick what they want to receive in terms of the criticality. So a two-step criticality gets defined here, and then the notifications get defined here as to what you want to receive in terms of what criticality. Really nice, simplistic way to show that. And then we have the reports. So the reports are really powerful reports. I can do all kinds of different things. So, you know, if I want to generate a report across my entire estate, so I can say what type of report. So we have the monthly comparison. We have monthly summary. So that's going to be a in-depth monthly summary about the information. I can ask for an exec brief. That's just high-level C-suite. I'm not too bothered about the weeds. Just give me the high-level data. And then we can ask for a technical deep dive. So if I go for a monthly summary, you know, I can say what reports go building level, client level, or organizational level. So we'll just do client levels as an example, and then we'll do this client, right, as an example. I can then do, actually, let's do Apex Innovation Labs. I can then say, provide that report, and now it's going to go off and analyze all of those sites for January, and then provide us a nice report based on what it sees. So here's the analysis. So basically what it's saying is, okay, across this estate, what was the total consumption, energy cost, peak demand, carbon emissions, how many anomalies? But here's the really powerful piece. So the Apex Innovation Lab portfolio consumes X amount in January. We're concerning concentration risk as Building B and Building E account for 91.7% of the total consumption, whilst Building A, C and D appear significantly underutilised or potentially offline. The portfolio experienced X amount of anomalies and FTD alerts, suggesting widespread operational inefficiencies that required immediate investigation, particularly in the two dormant buildings. Building B's disproportionate 48% consumption warrants urgent energy audit and load balancing reviews, whilst the minimal consumption in buildings A, B and C is less than 5% combined, indicates either exceptional efficiency or operational issues requiring verifications. Priority actions should focus on optimizing buildings B consumption patterns. How many anomalies were detected? And then a nice kind of energy performance recommendations for Apex Innovation Labs buildings. We then have a consumption analysis. So this is the total consumption across each site with a narrative again across each of those different charts and screens that we're looking at. We also have and show weather impact. So how much did weather impact the estate during that time? So the average temperature dropped from 6.9 to 4.4, resulted in heating degree days increasing from 265 to 345. Yep. indicating significantly colder conditions. This 30% increase would have driven heating substantially higher. Weather normalized performance, so provides that nice information there. And we can also see, again, across the entire portfolio, what the R-squared line of best fit looks like on that weather normalized data. We can also show the portfolio analysis in terms of the distribution. So clearly we can see building B and building E use a lot more energy in a disproportionate manner. Any energy performance, so we can see, this one we have some energy performance metrics here, so it's going to show you what they are in terms of the contribution, and then forecast validation, so anything around forecast and models that we have in terms of the forecast and accuracy. So really nice reports that we can do. We can run these at building level or estate level. We also have standard reports that are more around comparisons, right? And so we can run a comparison against two different periods. So here we're comparing January against February, and you can see period over period change. We have a daily comparison, so across those two months, what was the comparison between those days? We break that down hourly in terms of a heat map, and also a concentrated average weekly profile between those two periods as well. The reports are truly dynamic. We have a cost breakdown and the differences between how much the cost was between those 2 months, and then how much weather impacted that variation between those 2 months. So you can see here, as an example, in January 2025, we had 453 heating degree days, and in February we had only 360 heating degree days. So when we come to the breakdown tab, we need to understand how much weather contributed to that difference in terms of the comparison, and then just some nice recommendations based upon what that information has found. Again, they can be done at building level, client level, or organizational level. I think that's pretty much it. Lastly, just to finish, we can do these on demand, or we can do these as a scheduled report, which will just land in your inbox, which you can have a monthly report that gets created, or you can just run one on demand. So that's an overview of our platform. This stuff is really all around the user management, building management, and how we get data to and from the sites. And so I think at that point we'll probably leave it here. And yeah, if there's any questions, would love to hear them. But thank you very much for your time, for listening, and I'll see you guys in the next one.